In this video, we're going to take a look at one of the first synthesis reactions of a substitute alkane. We're going to take a look at the reaction of an alkyl halide. And we're going to see that alkyl halides are one of the most versatile functional groups of the list of functional groups that we've talked about today. And the reason for that, and I'm going to just kind of briefly show you, is they can be transformed into many other functional groups. For example, they can be transformed into alkenes. We'll see this reaction a little bit later on. They can be transformed into alcohols. Again, we're going to explore this reaction later on. They can be transformed into amines. They can be transformed into ether. So all the functional groups that we've looked at to date can be made from alkyl halides. And we're going to slowly explore those types of reactions in the next chapter. But in this chapter, we're going to talk about one of the fundamental reactions, and that is how to make alkanes out of alkyl halides. Now, alkanes are kind of tricky. They're fairly inert in their reactivity, and as such, they're kind of difficult to make. Not very many functional groups can be transformed into alkanes. Alkyl halides simply happen to be one of those functional groups. Now, it's not a direct reaction. You can't take an alkyl halide and directly make an alkane. To form an alkane, alkyl halides are first converted into what's called an organometallic reagent. An organometallic reagent. So organometallic reagents consist of carbon-metal bonds. So organocarbon, metallic metal. So organometallic bonds, so a carbon metal. And what happens is an alkyl halide can react with magnesium to form what's called a Grignard reagent, or it can react with lithium to form an organolithium reagent. So these are two metals that we're going to kind of focus on. Now, there's lots of other metals that make organometallic reagents, but these are the two kind of foundational organometallic reagents: Grignard reagents and organolithium reagents. We're going to take a look at each one of them. So how do you make a Grignard reagent? Well, you simply take an alkyl halide and you react it with magnesium. The solvent that's used is diethyl ether, and the conditions have to be very dry for this reaction to take place, and I'll talk about why that is in just a little bit. But you get this complex right here. It's RMgX. Now this is a salt. Grignard reagents are salts, which is why we're using diethyl ether. It's somewhat polar, right? It's a small ether, so it's somewhat polar, and it can actually stabilize the Grignard reagent. The electrons on the oxygen can donate to the magnesium to stabilize any positive charge that's associated with it. So this is called a Grignard reagent. It's called a Grignard reagent because it was discovered, I believe, in 1917 by a chemist by the name of Victor Grignard. It had actually been discovered many years before that, but nobody had a real clue as to what to do with Grignard reagents. And it was Victor Grignard that actually came up with a whole series of reactions in which these type of reagents were first in kind of the forefront of the reaction, and he won a Nobel Prize for that work. Now, we also have discovered that you can take an alkyl halide and treat it with lithium. Now, lithium is a little different because you actually need two equivalents of lithium. Oftentimes we don't show the two. We simply assume that there's an excess amount of lithium in here. And again, we're going to run the reaction in diethyl ether, and we produce RLI. Now, you also get a salt of a lithium halide salt from this, which is why you need to have two equivalents of lithium in the process. Now, the way these reagents are formed is through a process called free radical mechanism. Remember, free radical mechanism is the movement of one electron. So a free radical means that you have one unpaired electron. And if we take a look at, a kind of a generic mechanism of the formation of these organometallic reagents, the first step in terms of forming the Grignard reagent is we're going to take an alkyl halide and react it with magnesium. Now, magnesium has two electrons, two valence electrons, right? So it's going to donate one of those valence electrons. And what happens is you're going to donate that one electron. So notice I'm using the fishhook arrow with one electron from a carbon-halogen bond. Remember, carbon-halogen bonds are, we can break them relatively easily, and so we're going to combine the one electron from magnesium with one electron from that carbon-halogen bond, which means that there's going to be one electron left off, and that one electron is going to go to a carbon. So the result is a radical, right? So this carbon has an unpaired electron on it, plus now I formed a bond with a halogen, magnesium halogen bond, although it's a very polar bond, and magnesium still has one electron. So we have formed a radical plus this magnesium X with its lone pair of electron. And of course, we can combine that lone electron on the radical with the electron from magnesium, and we form our RMgX. This is what is referred to as a Grignard reagent. And oftentimes, you'll see this written several ways, where you have R minus Mg2 plus X minus, you have R Mg with a covalent bond, and an X. The magnesium has a +1 charge and the halogen has a minus charge. That's probably the best way. That's the way I like to think about it, because that carbon-magnesium bond is a covalent bond. An organometallic bond is a covalent bond. It is not an ionic bond. So that's an important feature of these, which is why they're somewhat soluble in polar solvents, but this is also why we use diethyl ether, right? It's not a very polar solvent. It's not water. There's a big reason for not using water or polar protic solvents, because we'll see that these are very strong bases. Now, to make our organolithium reagent, we take an alkyl halide plus lithium, but lithium only has one electron, so it donates its electron just like we saw before, and that lone electron goes on to my carbon, and I get lithium halide, a lithium halide salt, plus my radical. And now I need to react that radical with another equivalent of lithium. So this is where the two equivalents of lithium come in. And I form my carbon-lithium bond, and it results in my organolithium reagent. So both of these reagents are very strong bases. We saw this previously when talking about the acidity of amines. I remember I showed you that amines can be deprotonated by organolithium reagents. And so these are very strong bases. Again, this is one of the reasons why we don't use polar protic solvents. If there's a polar protic solvent around with a hydrogen available, it can act as an acid, and a reaction ensues, right? So that's something that we always have to keep in mind. How is the solvent going to play a role in it? I want it to solubilize it. I don't want it to react with it. But this means that these organometallic reagents will react with pretty much any acid, weak or strong. What kind of acids have we looked at so far? Well, we know that water is an acid. It's a weak acid, but it's acidic nonetheless. So these organometallic reagents will react with water. They'll react with alcohols. They'll react with amines, right? And so we don't want to use water or alcohols or amines as solvents unless we actually want them to react, right? Now, how do they react? Well, it's an acid-base reaction, and therefore I'm going to take, here I'm showing a Grignard reagent. It reacts with water. Water is the acid, the Grignard reagent's the base. So I can remove a proton from that water and form hydroxide ions. And the result is I form a new carbon-hydrogen bond. I also get a salt, magnesium halide hydroxide salt, right? Some mixture of salts. But the key is that this is a way of making alkanes. So notice I took an alkyl halide, I converted it to a Grignard or an organolithium, doesn't really matter which one, and then I react it with water and I produce an alkane. And this is um, an amazing way of making alkanes, very simple way of making alkanes. So let's look at some examples. In my first example, I have 2-bromopentane reacting with magnesium in diethyl ether, dry. Why do I say dry? Well, a lot of solvents pick up water, moisture. If water's in the diethyl ether, it's going to react with it right away. Now, in this particular reaction, I don't mind if it reacts with it, right? Because I'm going to form my Grignard reagent. So then I'm going to react it with water and I produce pentane. So I took 2-bromopentane and I produced pentane out of it. And of course I produced my salts as well, right? My magnesium bromide hydroxide salt. Another example is this reaction where I'm taking 1-methyl-1-chlorocyclopentane, react it with magnesium in ether. I make my Grignard. I can react the Grignard with methanol. And remember, methanol is a polar protic solvent, right? So it has a proton that it can give, and therefore it donates its proton, and I get methylcyclopentane. And of course, the salt would be magnesium chloride methoxide, OCH3, right? Now, one of the cool little tricks that I can do with this type of reaction is I can take not just an alkyl halide, but I can take an alkenyl halide, I can take an aryl halide. So a halogen coming off of an alkene is called an alkenyl halide. A halogen coming off of a benzene ring is called an aryl halide. And these react, so I can react this with lithium instead of magnesium. I'm using lithium here. Notice I don't put the 2 in front of the lithium because it is assumed that I have an excess amount of lithium. I form my organolithium reagent, and now what I'm going to do is instead of reacting it with water, I'm going to react it with D2O. So this is called heavy water, deuterium oxide. So deuterium is hydrogen. It's just an isotope of hydrogen that's heavy. It has a neutron in it. And but the cool thing about deuterium is it behaves a little bit differently spectroscopically. So this is one way that I can actually add something and I can monitor it spectroscopically. What kind of spectroscopy can we be looking at? NMR spectroscopy. Remember, deuterium is silent in the NMR of protons, and therefore I can make deuterated compounds, right? So it reacts the same ways. Its reactivity is very similar to that of water. not exactly similar, but similar enough, and we make deuterated compounds. So here I've made deuterated to butene. So 2-deutero-2-butene. And that deuterium is not going to show up in the proton NMR spectrum. But the other proton on the other sp2 carbon will show up, and there's all sorts of things that we can explore using this kind of methodology. So here we see a reaction of an alkyl halide forming a Grignard or an organolithium, reacting with a polar protic solvent to form alkanes. We can make alkanes, we can make deuterated alkanes, we can make alkenes, we can make deuterated alkenes. So there's all sorts of possibilities in this one type of reaction.